Okay, so now that we have all these differentiation tools, meaning we can find the rates of changes of a lot of functions, the natural question arises. If I give you a derivative, f prime of x, maybe we call it something like 2x cubed minus 7x, can I go back up the ladder and find f of x? That's a natural question. Can we undo the process that we did to get the derivative? And that's exactly what antidifferentiation is. We're going to study that today, and we're going to learn about that in the indefinite integral, which we're going to come to know and love as just this reverse process. So let's get into it. Okay, let's go ahead and try a first example right here. So if we read this, this says find the antiderivative of the function 3x squared plus 4x minus 2. Now remember, these two things right here, the dx and the integral sign, are just quotation marks for us saying, hey, find the item that we derived in order to land on this. So if we were going to go ahead and attack this, what we could do is just think, what did I have to derive to get each of these individual terms? So for instance, what could I have derived to get 3x squared? Well, it turns out x cubed is a really good option. And you can always go back and check it. If I derive x cubed, we'll bring down the 3 and subtract 1 from the power, so boom, we do land on that. Over here, maybe a little bit more complicated. What can I derive to get a 4x? Well, I know I have to have one more power up there, so I'd have an x squared. Well, when I derive that, the 2 comes down, and I landed on a 4, so I better have had a 2 in front. So 2x squared, when I derive that, I get a 4x. Maybe nicest of them all, if I just have a minus 2, the thing I derived to get that minus 2 would just be a minus 2x. Now the only other thing that we have to remember is that I could have had any single constant out here, and when I derived it, it would have went away, so we have to put a plus c at the end of it. Because once I derive a constant, it goes away. And it turns out that this right here ends up being my answer. Now we do have some shortcuts that we're about to get to, so hold on tight. Okay, so now let's talk about some shortcuts that we can use to help us out with this anti-differentiation process. Now the first one is going to be, what if I encounter x to some power? And we're going to put a little stipulation that the power can't be to the negative 1. So we're going to go ahead and say n not equal to negative 1. We'll cover that case later down here. Well, if I have x to some power of n, and I'm anti-deriving it, meaning I'm trying to find what I derived to get x to the n, it turns out that we're just going to have to add 1 to the power, so x to the n plus 1, but then we're going to have to adjust out front. Now the way we adjust, unlike deriving, is we're going to put it as 1 over n plus 1, and plus c as always. Now the reason this makes sense is as follows. If I were to try to derive this, first off the constant would go away, but second off, this n plus 1 would come down front, but then they'd cancel out. N plus 1 divided by n plus 1 would just be 1. So then we just have an x to the n plus 1 minus 1, or just x to the n power. So we do get right back where we started. Now, you might be wondering what this k is. Let's pretend k is just any number, just a number. Well, this rule's kind of nice. If you're integrating a number or find the antiderivative of just a constant, all it is that number times x. And then, as always, plus c, because I could derive that away, no problem. Now, these two end up being just a little bit trickier, so let's go ahead and go over them. If I'm asking you to find the antiderivative of 1 over x, with respect to x, kind of got our quotation marks around, we'd have to think, what can I derive to get 1 over x? It turns out that this leads us to the natural log of x. Now we have to include the absolute value bars. That's just a little bit of math etiquette. So go ahead and throw that on there, and then remember the plus c. So remember when we derived the natural log, we ended up getting the derivative of the inside, or just 1, divided by the original inside, or just x. So that really did lead us to 1 over x. Last rule that might come off a little tricky is what if I ask you to find the antiderivative of e to some power times x? So e to the ax, where a is a number. Well, what we could land on here, and if I got e to the ax, remember the derivative of e to the ax is a times e to the ax. So what we could do is say that the integral, or the antiderivative of e to the ax, ends up being the same thing, e to the ax, divided by a, and then plus c. These right here are going to be our shortcuts and the bulk of what we really care about in section 5.1. So if you have these down, you're off to the races. These are really good, really important things to have down. So let's go ahead and try a couple more example problems with these in mind. In particular, these last two do take a little bit of getting used to, but keep on practicing, they'll start to come easy for you. Okay, so now let's go ahead and practice some examples. You'll see that I got one nicer example, and then one a little bit contrived, but this will end up being a nice one for us once we're used to the process. So, first problem, find the antiderivative of 6x to the 7th. Now, one thing that's helpful, if we ever have a constant, like the 6 multiplied by something with x, we can always actually just factor out that 6. And we'll end up at the same thing. So these two are the same thing. Now the reason this might be helpful, let's say you have a ton of different things with a common factor and want to pull it out to make it simpler, but more importantly, with this x to the 7th, now we can use our rule. So, the antiderivative of x to the 7th ends up being, I'll copy the 6, well, we add 1 to the power, so x to the 8th, and then we divide by that power, times 1 over 8. Now, we have to remember the plus c. Always remember the plus c. It's really easy to forget. Unfortunately, it's pretty common mistake. Last but not least, all we have to do is multiply in. Now, what we'll end up with is 6 over 8, x to the 8th, plus 6 times c. Now the c was just a constant, remember. So if I multiply 6 times that constant, it will just be another constant. So we don't even really have to worry about this 6 right here. The c will just kind of absorb it up. So last thing to do is simplify. 6 over 8 becomes 3 over 4, x to the 8th, and then plus c. Ding, 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 ding. Final answer. By the way, you check if this is the right answer. If you derive this, you should land on this. And notice if we did derive it, so maybe I'll derive it in green real quick. I'd have, bring the 8 down front, so we get 24 over 4 x to the 8 minus 1, or the 7th power, plus 0. So, simplifying these guys out, we end up with just 6x to the 7th, which is exactly what we had to start with. So you can always check it by deriving your answer, and see if you get the original thing. Last example we'll do on this board, we have 5 divided by the square root of x plus 3. We're finding the antiderivative of this. Now, just like when we were deriving, these square root notation, the square root notation isn't too helpful for us. So the first thing I'm going to do in example 2 is to rewrite it. Let's go 5x to the negative 1/2 plus 3 dx. Well, now I can go ahead and use my power rule on it. So once you get pretty good, you don't really have to factor out like we did up here. Similar to how when you got good at deriving, you just kind of did the multiplication in your head. So let's go ahead and try that right here. When I find the antiderivative of this thing, when I tackle this term, remember I add 1 to the power, so I'll get x to the positive 1/2 after I add 1. The 5 gets copied down. Whoopsies, I'll move it over just a little bit for now. And then I divide by the same power. So 1 over positive 1/2. So that's just our power rule. Remember, add 1 to the power, and then divide by the power you landed on. This 3 isn't too harmful. All the integral of a constant becomes, or the antiderivative, is just the number with an x attached. And then last but not least, don't forget to add a c. Doing some simplifying, 5 times 1 divided by 1/2, well, 1 divided by 1/2 is just 2. What we'd end up with is just a 10 out front. X to the 1/2, and then I'll copy down the rest. Plus 3x plus c. There's your answer. And you can go ahead and derive it if you did want to check. And yet again, you would land on the original thing. Okay, let's keep rolling with some examples right here, incorporating our other shortcuts. So, for instance, in this problem right here, we have find the antiderivative of 7 divided by x plus 8x. Now, whenever you see 7 divided by x, or 7 times x to the -1 power, we have to know it's a little bit different than our power rule. Whenever you're dividing by x, we're actually going to use the natural log rule. Because remember, the derivative of natural log of x became 1 over x. So now we're going the other way with it. So that's what we're going to use right here. One thing that might be helpful, remember anytime you have a constant, you can just copy it down, would be this. Copy down the constant on top, and then find the integral of 1 over x. That ends up being just natural log of x. Plus 8x, we need to find the antiderivative of 8x. We have a basic power rule right here, so now we're in our wheelhouse. We add 1 to the power. First off, we copy down the constant. Then we add 1 to the power. And then divide by that same power, or multiply by 1 over that power. And last but not least, never forget it, plus c. So, in effect, what we have right here, once we go ahead and simplify out, is 7 times the natural log of x plus 4x squared plus c. That's our answer. If you're still worried about the 7 over an x, let's talk about it a little bit real quick. If I had in red the integral of 7 over x, what I could do is, remember, I could factor out the power, or the constant. So I could have 7 times the integral of 1 over x dx. Now when I derive 1 over x dx, I end up with natural log of x, but I always had that 7 out front to begin with. So we'd have 7 natural log of x and then plus c. So that's the reasoning there as to why we get 7 natural log of x. Don't want anybody to be confused on that guy. It's really, natural log is actually one of the nicest rules once we get used to it. Give me a little bit more room by erasing. Let's tackle this last one right here. Find the antiderivative of 5 times e to the 4x dx. Now for this one, I'm going to go ahead and factor out the constant. Remember, you can do this. Once you're quick with it, you don't have to, but I'm going to go ahead and do it for our own understanding. Okay, so now it's 5 times the antiderivative of e to the 4x. Well, the rule for this states, first off, copying down the 5, that it's just the original thing. So e to the 4x divided by 4, whatever that number was. Now yet again, remember the plus c. And then all we have to do, clean it up a little bit. It probably looks a little nicer if we write it as 5/4 times e to the 4x plus c. And that right there should do it for us. So now that we've got a little practice using those 4 shortcut rules, go ahead and look at your examples and really try to work some on your own using those rules. And remember, if you're ever worried, you can always factor out a common factor, like the 5 right here, and you can actually even kind of split it up term by term, kind of like we did here. We didn't tackle this thing all at once. We said let's find the antiderivative of 7 over x, and then the antiderivative of 8x. And that got us to our final answer. And as always, remember the plus C. Hey, so thanks for tuning in. Just wanted to give you a quick rundown on antiderivatives and what we covered today. So, first off, if you're given a function and asked to find the antiderivative, or the integral of it, the first thing you should think is, what did I derive, or what did I have to derive in order to get this function? That's going to be the driving thought behind your solving the answer. Now, while thinking about that, these shortcuts help. So, for instance, the big one for us is that the integral of x to some power, and always remember the dx, ended up being add 1 to the power, x to the n plus 1, and then divide by that, now power. So then divide by the power we landed on. And last but not least, plus c. As the third tip says, always remember the plus c. By the way, this is going to become known as our integration power rule. So just like we leaned heavily on the power rule for deriving, this is going to be our workhorse for the next chapter. So, hopefully this was an enjoyable section. Go ahead and try your homework out for yourself. Please come talk to me if you need anything. Thanks.